So you can see me rushing up here. I have way too many slides, way too much content. I will not be able to touch it. Really, to do this justice would take a half an hour. I'll breeze through it. So what this presentation is about is we are in pre-phase A. We are architecting this mission. We are trying to figure out how can we deliver the most to the community. And part of that is to really, I mean, when I say the word efficiently, I'm really talking about cost efficiency. LExSO is about a LRO class mission. So therefore we need to be as efficient as LRO and yet provide greater capability. Definitely a lot more people contributed to this. I just put my name on the front because I'm speaking, but there are a lot of people behind the scenes who provided me charts. You'll see Jesse Leitner and Rich Burns of SSMO really helped in giving the history of all the experiences and operating missions. And that's somewhat captured here as I breeze through it. So when we think about spacecraft longevity, we really heard from the community through the ClockSat report and also directly from the community that the great thing about LRO is that it keeps lasting, right? You saw to 2028. Well, LRO was a 14-month mission and it was single string and it was Class C. When most people think about longevity, they think of, well, let's up the mission class. The minus side of upping the mission class is you spend an awful lot more money just dealing with the mission class requirements. This presentation is, hey, can we think about a lower mission class, lower some of the overhead, make sure we have enough money or ample money to develop the science measurement instruments, which is really the focus of any space mission. And so you'll see, if we think about mission class, what are things that are Class A? You think of Hubble, you think of James Webb. If you think about Class B, most of the missions at Goddard are Class B. It's the most common mission class for things that you really want to survive. GOES is there, TDRS, comm satellite, MAVEN, Discovery, JPSS, a weather satellite, and OSIRIS-REx, New Frontiers. Those are all fairly expensive missions. Those are above the class of what LExSO is, maybe with the exception of MAVEN. Class C, well, really there's this sweet spot where you can do a lot for less money. And you can see of the 4 Class C mission, 3 are still operating well beyond their mission life. Icon has failed. It did last its mission life, but failed not too far after. And then you see Class D, and in fact, 3 of the 4 Class D mission listed there are still operating. LADI has re-impacted the moon. So when we think about classes versus risk posture, we all understand all the single point failures that were involved in James Webb Space Telescope. The likelihood of James Webb Space Telescope truly deploying and getting to the stage that we're seeing fantastic science from it today was not at all guaranteed. Certainly every effort was made to retire the risk as low as it could be, but it still was a fairly risky mission. There are a lot of Class D missions that are flown that aren't as risky, and it is possible to have a lower risk mission at a lower class. What is mission insurance? Jesse Leitner has really been pushing the on-orbit validation side of mission assurance. We really should be looking at components that have already flown and already been demonstrated and are showing that longevity ahead of, are we going to build them from mil-spec parts, but maybe we're going to screw up the design because it's low TRL and we missed a worst case analysis. Reliability. If you design it for 3 to 5 years, it's going to last well beyond it, as long as you take into account radiation, that you have enough consumables, and that you've done your worst case analyses correctly. and done enough testing to reveal a workmanship issue. And most mission failures are when we don't do enough testing to reveal a workmanship issue, or we miss a worst case analysis, or do it incorrectly. So how do you design things to be robust? You want to design for manufacturability, so we don't build in workmanship errors. We also want to think about what are the creative ways we can add in selective redundancy. Can we make the key components fault tolerant? Can we design for minimum risk? Can we design to have the ability to reset, or and can we degrade gracefully? So what does it mean? We think we can build missions with long life without spending a mint. And that's what this paper is about. And you'll see a couple of charts and a few slides that will show some of the components that we decided to implement in the architecture of LExSO for selective redundancy. This chart is out of an aerospace report. And one of the things that's kind of interesting, wish I had a laser pointer, is there's a whole lot more missions that are above the line than below the line. And particularly once you see above 3 years in mission life, a great majority of missions are lasting 5 to 10 years. This is also a very interesting chart. One of the notes here is military satellites and NASA satellites are more reliable than commercial satellites slightly. But you can see in the 3 to 5 year range, you are certainly going to get pretty high percentages for 10 years of lifetime, just in general. And this doesn't really control for, did I run out of fuel? If you look at in-house buses that Goddard has built, and you look at reliability of in-house buses, LRO, when it does fail, is probably going to fail because of consumables rather than essentially failing due to electronics failure. And you can see here at year 14, which LRO's in this year, it would be predicted on a single string bus made in-house to it's got 89% chance of reaching this stage based on actual as flown numbers. So what are the components that drive mission lifetime? You can see ACS components, mechanisms, EPS components, telecom, and those are missions that are impacted by semi-failures. And you can see, by the way, that LRO is on 3 of those columns. There are things that we are doing with LRO right now to preserve its life. And these are some of the areas that we're managing, let's say it that way. So what did we look at when we wanted to architect LExSO? We want to build in redundancy within our IMU. We're doing it internally in a unit. We want to have redundant star trackers. Core sun sensors, always want to have redundant reaction wheels. Almost every mission builds in extra battery capacity. The fact that LRO is still flying today is our battery engineer wanted to over-design LRO's battery for 14 months. So think about that when you're doing architecting missions. We also have an oversized solar array. Lately, we've been seeing some comm failures. So LExSO has dual string comm paths. We are currently S-band for commanding, even though it says X here. Always have redundancy in thrusters. And we're also going to have a redundant oscillator. And my very last slide is now coming up. Sorry to take so long. If we just blindly put higher mission classes on missions, we're going to spend a lot of overhead, and we're going to make scientific payloads smaller by definition. If we're willing to live with, hey, can we do a Class C mission be really smart about our redundancy, be really smart about the way that we test it, I think that we can get a more cost-efficient mission for the future and provide better measurements over the course of the mission life. We've demonstrated at Goddard that Class C missions are going to exceed mission lifetimes. In-house ones, we've noted have very high reliability. I think that's all that I need to say, because I'll just repeat myself about selective redundancy.